Today's topic is another way to solve quadratic equations that we should try after factoring. So if factoring doesn't work, then we have a method called completing the square, which is a really nice way to solve some quadratics. So first of all, we haven't really talked about when can you and can't you use factoring. Factoring relies on two things. One, the quadratic has to have real solutions, meaning that if we did something like this, we couldn't factor that because it doesn't have any solutions. We also couldn't use completing the square for that. So that one's not really that important. But the other one we haven't talked about is if you do have solutions or x-intercepts, but they're not at nice numbers. So when we've been dealing with these, we always end up with x-intercepts that are like 2 or -7, or in the worst case, we'd get something like 5/3 or -7/5. But all of these are still what we call rational numbers. They're all expressible as fractions. What we can't do is factor anything that has irrational roots, or irrational solutions. So if we have a quadratic that has one x-intercept at, say, 1 plus the square root of 2, and another one at 3 plus the square root of 5, there's no way that we could solve that by factoring because these are what we call irrational numbers. They have square roots, or, things like pi are irrational, meaning that they have decimals that go on forever without repeating. So we have this method as a way to solve for cases that can't be factored. But you should look for factoring first, and most of the ones on these notes are solvable by factoring, so I'll probably show you just the comparison, and we'll look at a few that can't be solved by factoring. So the first one we have here, x squared equals 10x minus 9. If I move everything to one side and do x squared minus 10x plus 9 equals 0, then the first thing I should check is, can I factor this? I'm going to do that off to the side here in the glue here part. So my factor tree was not a diamond. It should be a 9. It should be 9. And my signs, my bigger number is negative, and they're the same sign, so they're both negative. So I can have 1 and 9, or 3 and 3 are the only factors, and all of these would be negative. So I can see that -1 and -9 are factors that create -10 in the middle. So I would just factor this as x minus 1 times x minus 9 is equal to 0. Then I know my solutions are +1 and +9, and I'm done. So that's how we should solve that one. It's particularly easy since a is equal to 1. I don't even need the area model or anything like that. I can just do my factors, find my -1 and -9, and jump straight to my solution. So I basically just need this work, not anything else. So I'm going to show you the steps of completing the square on this same problem, so hopefully that will help you see that it's better to do factoring when possible instead of completing the square. But we're going to follow the steps on the right here. Step 1, always look for a GCF first. We don't have to worry about that because a is equal to 1, so there's going to be no GCF. Step 2, we could technically use completing the square for any quadratic, as long as it has real solutions. But we're going to limit our uses in Algebra 1 to cases that are easy to use it for. So we're going to check. We only want to use it if a is equal to 1, which it is, and b is even, which it is. So this one is a good candidate for completing the square because those two conditions are true. In Algebra 2, you'll use completing the square for less friendly quadratics, but we want to keep it simple in Algebra 1 when we're just barely learning this technique. So step 3 is to rewrite the equation, but with the constant on the other side. So we're going to rewrite this as x squared minus 10x is equal to 9, -9. I'm actually also going to leave a little space here. So is equal to negative 9. So the reason that I left a space is the name, as it implies completing the square, is we're missing something here to create a perfect square trinomial. Remember that perfect square trinomials look like a squared plus 2ab plus b squared is equal to 0 or equal to y. So that's hopefully going to help you see why we want an a value of 1, so it's 1a squared, and this number we want to be even so that we have like an even number of ab's. So for example, if I had x plus 4 squared, I get 1x squared, and I get an even number of x's because I get 4x and 4x, and then I get 16. So we're trying to create something like this so that we can factor it into something like this. In this case, and to find this missing number, what I can do is I take negative 10 from the middle here, divide it by 2, and I get negative 5. So that means in my perfect square trinomial, I have x squared minus 5x plus this missing number. And that missing number has to be 5 squared, or negative 5 squared. So this missing number has to be 25, and it would create the perfect square x minus 5 squared, or x minus 5 times x minus 5. So to fill in this blank that I left on the left here, I need to put in a plus 25 to create a perfect square. But you know I'm not allowed to just add 25 on one side of an equation. If I add something to the left, we'll do this in pink since it's new, plus 25, I also have to add the same thing on the right side of the equation, or I unbalance that equation. It's not true anymore. So when I add 25 on the left to complete my square, I'm going to also add 25 on the right. The next step is to factor this as a perfect square trinomial, which would be x minus 5 squared is equal to negative 9 plus 25 is 16. Step 6 is we're going to solve this the way we would have solved a thing with a square in it at the very beginning of the year. Before we learned any fancy algebra stuff, we just followed the order of operations in reverse. So we had P, E, M, D, A, S, and we followed up the chain in order to solve equations. So to solve this, I have x minus 5 trapped in parentheses behind this exponent. So the only thing I can do here is square root both sides. So I'm going to square root the left and right side, and my square and square root cancel. So I'm left with just x minus 5 equals, and here's kind of a new thing. When we square root 16, we have to remember that there's actually two different options. I have 4 times 4, so positive 4, or negative 4 times negative 4. So the square root of 16 is positive 4 and negative 4. There's two different answers for that. So anytime you square root a number, you always need to put plus or minus that number. So plus or minus square root of 16, which we can just more simply write as plus or minus 4. And since this came out to be a perfect square, that means I could have factored this. So if I started with this method, this would be the point where I'd go, oh man, I could have factored it and it would have been way faster. So now to finish solving it, I have x, I need to get it by itself, so I add 5 to both sides, and we get x equals 5 plus or minus 4. But that's just two different numbers. Over here, I have 5 minus 4, and over here I have 5 plus 4. So my two solutions are 1 and 9, which are the exact same solutions that we got by factoring, except it was way faster by factoring. So compare the amount of work that we did here to the amount of work that we did here, and hopefully that will help you see why factoring is the better choice if you can factor the problem. You could use completing the square for this from the beginning, but it's not the best choice. So that's the process. We follow those steps, and we're going to go through a few more examples so that you can see how they work. On the ones that are factorable, I'm going to tweak them a little bit just so we can not have to worry about this comparison every time. Yeah. So the why for using this method is factoring didn't work, basically. So if we can factor, we should. And there's several ways of factoring. We have GCF, and we have special cases, and we have area model. So if none of those work, then we can go to this as our next method of choice, and then there's one remaining method that will always work, but it's the least elegant and not a good choice as a first stop, and it's called the quadratic formula. We'll learn that one shortly. So as it said on page 1, like it was in the steps, we only want to use this if A equals 1 and if B is even. Maybe at the end I'll show an example of where B isn't even, just so you can see why it's or A isn't 1, just so you can see why it's kind of ugly to deal with. All right, so this first problem is, I don't know if it's solvable by factoring. Let's see. We have 3x squared. We add 21x, so plus 6x. We subtract 30 minus 30 is equal to 0. Now we need to divide out our GCF from both sides. When we're completing the square, it's important that we don't just factor it out to the front. We actually have to divide it out of both sides because it'll get in the way when we're trying to move terms around like we did up in this example on the first page. So I divide by 3, I get x squared plus 2x minus 10 is equal to 0. So first thing I check real quick, can I factor it? If I do negative 10, I have my bigger one is positive, my other one's negative. So I have either negative 1, positive 10, or negative 2, positive 5. Neither of those gives me 2x in the middle. They give me 9x and 3x. So I cannot solve this by factoring, but A is equal to 1 and B is even. So this is a great candidate for completing the square. So step 1, I don't remember what the step numbers are actually, but the next thing I need to do is do x squared plus 2x. Then I'm going to put plus blank to leave a space for my missing term, equals, and I'm going to add 10 to both sides to put this over here. I'm also going to put plus blank on this side. So this blank is where I'm going to put the magic number that completes my perfect square trinomial. So I divide 2 by 2. So I do 2 divided by 2 and square it, I get 1. So my magic number that's missing on both sides is 1. And you can see, hopefully, x squared plus 2x plus 1, that is a perfect square trinomial of x plus 1. So we condense that down to x plus 1 squared is equal to 11. Now we can solve this by basic algebra, so we're going to square root both sides. We get x plus 1 equals, and this is where we have to remember that we have plus or minus the square root of 11. There's 2 options. The last step to get x by itself is to subtract 1 from both sides. So I get x equals negative 1 plus or minus the square root of 11. And since these are 2 irrational numbers, I don't actually need to do anything more than that. I can call this my answer, and that's good. I could also write it using set notation as x equals, and then curly brackets, negative 1 minus root 11, comma, negative 1 plus root 11. That means the same thing if I list them out in set notation or do negative 1 plus or minus root 11. Notice that in the example we did on the first page, though, I can't leave it as negative as 5 plus or minus 4. Since those are both integers, I can simplify that and I can make it 1 and 9. So I don't leave it as plus or minus if these are both rational numbers. I only leave it as plus or minus if I have a rational and irrational number being added together, because they can't add together. They're different sizes. All right, the next one, we have x squared plus 6x plus 5 is equal to 0. So checking my factors, I have 5, and these are both positive. So 1 and 5 do add up to 6, so I should solve this by factoring. Solve by factoring. But let's pretend that it's slightly different and just take this 1 away. So then I have x squared plus 6x plus 4 equals 0. My factors of 4 are both positive, either 1 and 4 or 2 and 2. Neither of those adds up to the 6 that I need in the middle, so this one is not factorable. Since it's not factorable, I'm going to use completing the square, because a is equal to 1 and b is an even number. So we are going to do x squared plus 6x plus blank is equal to negative 4 plus blank. So see if you can figure out what number goes there. We're going to basically split this 6x into 3x and 3x. So my missing number at the end would be 3 squared, which is 9. So we add 9 to both sides, and then we condense our perfect square trinomial, or factor this as a perfect square trinomial, into x plus 3 squared equals negative 4 plus 9 is 5. Square rooting both sides, I get x plus 3 equals plus or minus the square root of 5. Then last step, subtracting 3, I get negative 3 plus or minus root 5. And that's how I would leave my answer. Remember that if the square root of 5 turned out to be a fraction or a whole number, you would need to actually get 2 different solutions and not leave it in a plus-minus version like this. All right, there's 3 more of these. Let's see which ones are factorable really quick. So we have x squared minus 10x minus 24 equals 0. So negative 24, that could be negative, or we need a positive and negative. So that could be negative 12 and positive 2. So this one does factor. This one, x squared minus 4x minus 32. So 32 could be a negative 8 and positive 4. So this one also does factor. And the last one, we have 9x squared minus 18x. And then subtracting 65, we get minus 72. So that's x squared minus 2x minus 8 equals 0. So that one we have negative 4 times positive 2, so this one also factors. So what we're going to do is tweak each of these to make sure they don't factor, and then I want you to try them on your own and then unpause the video if you need help with how to get through them or just to check your answers. So the first one, let's change this 24 to be, let's see, we had, we're trying to make 10, so let's make this just 22. On the second one, we need 32, so we need something that doesn't make 4. Let's just change this to 30. Changing it by 2 is pretty effective. And then on the last one, let's change this to 9. So make these 3 changes. Change this to 22, this to 30, and then we're making this 9, which I guess the change to the original problem would have been to change this, let's see, negative 7, and we tried to make negative 81. So that would be changing this to plus 84. 84, 91, 81. Change that to 74. I can math. Okay, change that to 74. So make those three changes and then go through and try to solve these three by completing the square, and then you can unpause and check with the work that I do. All right, so this first one we have x squared minus 10x plus blank equals, and this will be positive 22. So then we're going to fill in half of negative 10 squared. So that's negative 5 squared. So we're adding 25 on both sides. I made 47. 47's good. Okay. So then we have x minus 5 squared is equal to 47. We square root both sides, and we get x minus 5 equals plus or minus root 47. Then we add 5 to both sides, and our final answer would be x equals 5 plus or minus the square root of 47. So really quick before we do the other two, let's talk about what that means in terms of like solutions. So first of all, this 5 is my axis of symmetry. So 5 is my AOS. And then square root of 47 tells me that my two solutions are that far away to the left and the right. Square root of 47 is a little less than 7, because 7 squared is 49. So that means that my first solution is going to be over here at 11 point something, right? And my second one is about 7 to the left, so it's going to be at like negative 1.9 or 1.8, something like that. So that's what we're finding here by completing the square, is this is my axis of symmetry, and this is the distance away that the zeros are along the x-axis. All right, this one we changed this to 30. So this would be x squared minus 4x plus blank equals, and this would negative 30, so this would be positive 30 plus blank. That gives us x minus 2 squared, so we need a 4 here in order to complete that square, and a 4 here. So x minus 2 squared equals 34. X minus 2 equals plus or minus root 34. And then x equals 2 plus or minus root 34. I didn't really try when I made up these numbers, but I should have probably made one where the radical could be simplified. So if this square root of 34 was, say, like square root of 32 instead. So I'm going to go back. I know you did it with this number, but let me go back and change it to make this so it'll be 32. So we're going to change this one more time. And we're going to make the 30 into a 28. So we're going to make this minus 28, which gives us 28 plus 4. Then I get x minus 2 squared equals 32. X minus 2 equals plus or minus root 32. And then I get x equals 2 plus or minus root 32. So this answer isn't quite finished because square root of 32 can be simplified. 32, if you remember simplifying radicals, is 2 times 16, and 16 is 4 times 4, meaning I can simplify this as x equals 2 plus or minus 4 root 2. So yeah, that one we may also need to use our simplifying radicals tool as we're writing the answers for these. And then the last one, we changed this to 74 so that this would be x squared minus 2x minus 9. So that would be x squared minus 2x plus blank is equal to 9 plus blank. So the perfect square I'm trying to make here is x minus 1 squared, meaning I need to add 1 here and 1 here. So x minus 1 squared is equal to 10. That gives me x minus 1 equals plus or minus root 10. And my final answer would be x equals positive 1 plus or minus root 10. So that's some examples of how we can use this method. I said I would do one at the end where it wasn't pretty, just to show you what it looks like. So let's do that, and then we'll wrap up. So let's say we had 3x squared plus 5x minus 12. Oh, yeah, minus 12 equals 0. And we want to solve this by completing the square. The first thing we would do is, since a isn't 1, we have to divide everything by 3. That gives us x squared plus 5/3 x minus 4 equals 0. Now I need to add 4. We follow the same steps as before. Over 5/3 x equals positive 4. But now when I'm creating my perfect square trinomial, I'm going to get some pretty ugly numbers because I'm going to take half of 5/3 and square it. So that means I have x squared plus 5/3 x plus blank equals 4 plus blank. And my 5/3, so if I do 5/3 divided by 2, that's 5/6, and then I need to square that. So my perfect square is x plus 5/6 squared, and my missing constant is 25/36. So I need to add that to both sides. So hopefully you can see why this is getting pretty ugly. I need to add this 4 and this 25/36. So 36 times 4 is 4, 2, that's 12, so 144. So this actually ended up being a lot nicer than I intended. We have 144/36. So then we square root both sides. 169. Whoops, not 144. I didn't add the 25/36. 169/36. Still a lot nicer than I intended because these are perfect squares. That wouldn't usually actually happen. The bottom should be a perfect square, but not the top. That was just lucky. So we get x plus 5/6 equals plus or minus the square root of 169 is 13, and the square root of 36 is 6. So I get x plus 5/6 equals plus or minus 13/6. So I actually made up one that could have been factored, of course. Just my luck. I make up random numbers and it ends up being factorable. Negative 5/6 plus or minus 13/6. Now, since these are both rational numbers, I would have to break that out into two real solutions, like final solutions, which is negative 5/6 minus 13/6. That's negative 18/6. And negative 5 plus 13, that would be positive 8/6. So my solutions ended up being negative 3 and positive 4/3. So definitely could have solved that one by factoring because there's no radicals in the answer. So yeah, I just made up random numbers to make it ugly, but you can still see that the process of completing the square gets really ugly when we don't have those two criteria that we wanted to look for. So yeah, that's our notes for today. We'll learn the last method, which is the quadratic formula, in the near future.